Hi, in this video we'll explore how PyTorch represents images as tensors and handles them for deep learning. Our learning goals are to gain familiarity with tensors in Torch, understand the need for data type transformation and scaling, and to understand how to move Torch tensors between devices. We saw this image in the previous lecture. We explored how the color channels correspond to a stack of matrices. The term that we use in PyTorch for matrices that can have any number of dimensions is that of tensors. We'll talk a lot about this concept in this video. So the question that might first pop into your mind is, why do we use PyTorch tensors? What makes them different from the n-dimensional arrays that we have in NumPy? We will see that what we can do with Torch, we can also do in NumPy in most cases. So there are two main differences between the Torch library and NumPy. The first one is that PyTorch tensors can run on graphics processing units or tensor processing units, speeding up training and inference. There is a lot of code that it's implemented on PyTorch using the CUDA programming language from NVIDIA. This is something that we don't have to code directly when we use the PyTorch library, but it gets called under the hood. This is something that we have in PyTorch that is not available on regular NumPy. Another very important feature is that we can do automatic grading computation. This is called Autograd or AutoDiff, and this enables us to compute the derivatives of the loss function with respect to the weights. This is something that we do to update the weights of the models and to actually do learning when we do the training of a neural network. This is necessary for training neural networks when we use the stochastic gradient descent algorithm that we're going to discuss with some detail. So this diagram illustrates the architectural differences between CPUs and GPUs. CPUs contain few cores that are optimized for sequential processing with large cache memory. CPUs are ideal for running programs that might be interrupted during their execution, like operating systems. On the other hand, GPUs contain hundreds of simpler cores designed for parallel operations. They were originally designed for processing graphics, which depends a lot on linear algebra. This is why GPUs excel at matrix operations in deep learning. They can process many pixels at once. Different cores in a GPU can take different chunks of a large image and process it faster than doing the same operations on the lower number of cores that we have on most CPUs. This slide demonstrates PyTorch GPU acceleration in practice. The code shows a digit classification model with MNIST dimensions of 28 times 28, and we have 10 classes in the output. The device selection ensures that the code works on machines with or without GPU. Let's take a look at it line by line. Notice that we import the NN model from Torch to create neural networks. This is a wrapper class for the most important models, the most important features that we would use for creating neural networks. So we're going to have things like the linear layer, the activation functions, operations like flattening, implemented as NN model. It's a very convenient interface that wraps together the parameters of the model and the features that we need to multiply times them. We see in this code that we create a linear layer that takes a flattened image of 784 pixels, this is 28 times 28, and outputs 10 values. We check the GPU availability with the command CUDA.isAvailable. CUDA stands for Compute unified device architecture, and this is a technology that NVIDIA developed for programming GPUs. Whenever you read the word CUDA in the PyTorch documentation, you can think of it as a stand-in for GPU. When we use toDevice, we can move both the model and the input data to the GPU. And then we run inference on the GPU with model tensor. There are some common mistakes to avoid. The first one is forgetting to move the input data to the GPU, because we need to have both the model and the features, the input data, on the same device in order for us to do any operation between model and data. So we need to be very explicit about this. We need to assign both the model and the tensor to the GPU. This is something that will move the memory that we have for the model to the GPU, and it will also move the memory of the tensor to the GPU. It's also important for us to assign the result of toDevice back to the variable, and it's also important for us to check if we have the GPU available first. In the next slide, we'll see why we need to move tensors back to CPU for certain operations. So here we see why and how to move tensors back to CPU, a very common example, and that is of visualization. Visualization libraries like matplotlib operate on the CPU. So if we try to plot directly a tensor that we have on the GPU, this will fail. We move tensors to the CPU using the command .to, passing the string CPU, or calling the method CPU. This transfer creates a copy of the tensor. And it's important for us to keep this data movement in mind to avoid runtime errors. The example shows first when we do PLT show scores failing because scores is on the GPU, and then when we do PLT show scores to string CPU, this is working correctly because now we have moved the data back to the CPU. So key points to remember: the GPU is for quick computation and the CPU is for visualization and input-output operations. The data movement between the CPU and the GPU has an overhead. It's an operation that is relatively slow. So it's good for us to be mindful about this and also to keep track of the tensor locations that we have in our code. This slide demonstrates a very common workflow pattern in PyTorch. We compute on the GPU and then we visualize outputs and results on the CPU. So matrix multiplications with very large matrices can have a speedup from 50 to 200 times when run on powerful CPUs versus powerful GPUs. This is important as this is the most common operation that we will be doing during training or the execution of an already trained neural network. Here you see examples of a speedup on a modest GPU that we can get for free from Kaggle. We're going to be using this environment very often in our course. You can click on the link on the slides to explore this code in detail. In this slide, we're going to pick apart one of the most important features of PyTorch, which is Autograd. Autograd gives PyTorch the ability to automatically compute gradients. We need these gradients to update the weights of our model. And these gradients are the values of the loss function with respect to the weights themselves. Here we see a minimal example with the absolute error loss. We compute the partial derivative of L with respect to W1 using Autograd. We start by importing Torch, which loads the library. Then we have this assignment of W1 equal torch, tensor, and passing the little list with 4.0. And here we're being explicit about something. I'm highlighting something important here. And that is that the weight has the parameter requires grad equal true. Requires grad equal true tells PyTorch to track operations on W1 so that the gradients can be computed. Then we have on the next line this x1 torch tensor 5.0 with requires grad equals false. This is an input feature. This could be like the intensity value of a pixel. Since we have requires grad equals false, PyTorch will not track the gradient of this variable. It's not necessary because we're not going to be updating the feature. We're only going to be updating the weights of the model. We see that we also have requires grad equals false for this y equal torch tensor 6.0. This is also not tracked for the gradient because it does not need to be adjusted during training. This is the target value that we're trying to predict. We're trying to adjust our model so that it produces a value close to this target. Then we have this L value for the loss, which computes the absolute difference of the weight times the feature minus the target. This defines the quantity that we want to differentiate with respect to W1. This is where we're going to be applying calculus and the chain rule in order to find out what is the gradient. And then you see something interesting. When we print L.item, this will extract the scalar value of the loss. And when we do the querying of requires grad on L, we find out that this is true. This particular variable already has requires grad equal true, even though we didn't explicitly set it up. And this is because L depends on W1, which is a variable on which we did set up requires grad equal true. So as this L value has this tracking of the gradient, we can call backward. Backward is this method that performs backpropagation to calculate the partial derivative of L with respect to W1. PyTorch will use L's computation graph, which is shown in the right. Like this diagram that we see here tracks every single operation that was done on W1. And you see that as we had requires grad equal true, everything that was done on this particular tensor, the multiplication, the subtraction, the absolute value has been tracked. This is called a computation graph and is created automatically by PyTorch. So we finally can access the gradient by querying it. We can do w1.grad, and this will show the gradient of the loss with respect to 1. And this is the magic that PyTorch does for us. If we didn't have this Autograd functionality, we will need to find a different way to compute these derivatives. So in PyTorch, we have image tensors that follow the format NCHW, where N is the batch size, is the number of images, C is the number of channels, which is 1 for grayscale, 3 for RGB, H is the height in pixels, and W is the width in pixels. A quick note that is relevant is that the number of dimensions that we have stacked is usually called the rank of a tensor. You will see this terminology in the documentation of PyTorch very often. We can query the rank of a tensor with the dim function in PyTorch. This particular tensor has rank 3 when it does not include the batch dimension, and rank 4 when it includes it. We have make it have a batch dimension of 1 when we call onSqueeze0 on it. So PyTorch tensors also have a different dimension order, which is CHW, channels, height, and width. This is different than the order that we have in NumPy, which is height, width, and then channels. The toImage function handles a conversion from NumPy's format to PyTorch format. The shape output that we have here as 3, 1200, 1800 reflects 3 RGB channels, 1200 pixels in height, and 1800 pixels in width. A common pitfall is that Matplotlib expects the NumPy format, not the PyTorch format. So we need to use this function called permute and pass 1, 2, 0 to rearrange the dimensions for visualization. 1 is going to tell PyTorch to rearrange the tensor so that height comes first, 2 so that width comes second, and 0 so that the channels come last. It's also important to discuss the issue of numerical stability. It's one of the main challenges that we face when we do deep learning. We want our algorithms to be as numerically stable as possible. Numerical stability refers to how sensitive an algorithm's results are to small changes or errors in the input values and intermediate calculations. A numerically stable algorithm will produce outputs that do not change dramatically due to tiny variations in input data or the floating point rounding errors that occur in computers. A stable algorithm tends to keep small errors small rather than making them blow up and amplifying them, which is what we want to have reliable and accurate results over the course of computations. This slide shows why scaling input values is important for numerical stability, especially in operations commonly used in deep learning. So here we have a pixel represented as 3 unsigned integer values, 255, 204, 170, which are common for image data. Directly using these large integers in nonlinear operations like exponentials can lead to numerical overflow. We convert and scale these integers to float by dividing them by 255, the maximum value that we can represent to uint8. Now we get values that are like 1.0, 0.8, 0.66. This puts the pixel values in a range that's more manageable for many mathematical operations, like the e to the power of x function, which we implement element-wise with torch.exp. If we apply this function directly to the original value integers, this results in infinity, since the exponent of 255 and similar values are astronomically large and exceed the range that we have for the floating point limits. When applying torch.exp to the scale values, this stays in a reasonable range. For example, exp of 1.0 is about 2.71, the Euler number, which is perfectly safe and stable. This demonstrates why transforming image data into a normalized floating point range before performing complex operations is a common and important step, especially to ensure stable and reliable training of neural networks. This exp function is something that we'll be using thousands of times when we train a neural network. So this slide demonstrates why we scale pixel values for numerical stability. We saw the key steps of creating a tensor with RGB values in the range of 0 to 255, converting it to float and scaling it to the range of 0 to 1. And we compare the exponential operations on raw versus scale values. The example reveals that the raw values will overflow when we run them on 255, 204, and 170, but that the scale values will produce stable results. The division by 255 normalizes the pixel intensities. It's a very common issue in practice to forget to scale the input images, or using the wrong data type, using the unsigned integer 8 instead of float 32 or float 16. it's very important to be aware that we need to handle this overflow in activation functions. And we'll see that many of the functions that we will use in PyTorch come with numerical tricks so that they are more numerically stable. For example, we will be using a function called log softmax very often that is more numerically stable than the softmax function that is more interpretable and easier for us to understand. This pattern of preferring stable computations is something that is prevalent in deep learning because we want to avoid these gradient explosion issues where we have numbers that are too big for us to represent in the numerical ranges that we have in our computers. Okay, so let's review some key points about PyTorch tensors. There are three main advantages of PyTorch. GPU acceleration is great for faster computation. We have this automatic gradient tracking for training that is very convenient when we are creating a new neural network. And we have two critical implementation details. One is the dimension ordering. PyTorch uses the format batch, channels, height, and width, whereas NumPy uses height, width, and channels. The order matters for the conversion between frameworks, and this is done with the toImage function. The numerical stability issue is also quite important. We want to scale pixel values in the range that is originally from 0 to 255 to 0 to 1. And we also want to convert the unsigned integer 8 that is the default for the data that we ingest as a PNG or a JPEG image into flow32. We want to prevent the overflow in operations like the exponential. And this is done with this scaling. It's a very common failure point to forget to move tensors to the correct device, to mix up the dimension orders, and also to forget to scale these input values. These are things that we will practice in the Practical Jupyter notebook that comes with the lesson. We're going to be practicing tensor operations, we're going to explore Autograd, and we're going to try to build a simple but complete training pipeline.